Hi, this is Sieg Schmalz, Applications Engineer at Microchip Technology. In the previous videos of this series, I described TIE Jitter of a real, non-ideal waveform as the sum of its Fourier components. These Fourier components have different amplitudes and frequencies. But how do we actually measure TIE Jitter in such a way as to give us a meaningful value we can work with to describe the quality of a clock? The answer is that we use a phase noise analyzer. Now, you know why I spent all that time in the previous videos describing spectral density, phase noise, and so forth. We have the basic understanding we need from the previous videos, so I am going to discuss this in slightly more mathematical terms now. Please keep in mind during this discussion that when I use the term jitter, I am referring to TIE jitter, or time interval error jitter, which is also called phase jitter, not other types of jitter that we will be discussing in future videos. A spectrum analyzer can calculate the power of voltage domain noise by integrating over a frequency range to get the value in terms of volt squared, which of course is related to power expressed in dBm via the formula you can see here. We then take the square root of this to give the voltage noise in terms of RMS volts. We use a similar process with a phase noise analyzer to calculate the phase noise power. Just as a spectrum analyzer is used to calculate RMS volts, we integrate phase noise power spectral density over a given band of frequency offsets from the carrier, and then we derive the RMS phase noise amplitude of a real clock. Just as noise in terms of RMS volts from a spectrum analyzer depends on the frequency range over which it is integrated, the noise in terms of RMS phase from a phase noise analyzer is directly related to the integration band that is used. Furthermore, phase noise analyzers translate the RMS phase noise from units of radians to units of seconds. For example, if a 10 megahertz clock has RMS phase noise of 2 pi radians divided by 2000, the phase noise analyzer reports that in terms of the period of the clock divided by 2000. For a 10 megahertz clock, this is 100 nanoseconds divided by 2000, which is 50 picoseconds. The same RMS phase noise of 2 pi divided by 2000 is only 5 picoseconds for a clock that is 10 times faster, a 100 megahertz clock, because it is 10 nanoseconds divided by 2000. Timing datasheets specify jitter in terms of picoseconds or femtoseconds RMS jitter, not radians, so we need to keep this conversion in mind. Now, just to review, why do we care about this? We need to keep in mind that if your clock source violates the jitter specifications, data errors can result. If the data error rate is large enough, your system may not function properly.